This is to go.
Take off in the middle.
No, I can't say anything.
So, we close this work. We don't really close yet, but so the last speaker of the workshop is Andreas, who's going to talk about scientists know less than nothing.
Okay, well, the title is actually a different one. This is the title. The mother of all protocols. So, yeah. So this one here, as you can see, this is from a publication in Bristol. It's a kind of a local newspaper. And they were quite delighted when I published a paper with two other guys about negative information, so they had a field day. So I'm not going to talk about that, but I will talk about this as a consequence. So, so the title, I think, of the presentation was the mother of our protocols restructuring quantum information's family tree, and for the purpose of this talk, I changed the subtitle to Quantum Coding for Dummies, and it's not so much because I think that you're all stupid, but because I want to say that, you know, this body of work culminating in this preprint, this body of work on quantum channel theory, is really much more simple than it is perceived. I mean, there's really only a very small number of rather primitive ideas behind it. So if you've ever tried to read one of these papers and failed, I would like to encourage you to read again, and maybe this particular one. So that's kind of the sum, but I will talk about lots of other related work of mine, of other people. So this particular one was written with Anura Abisinghe, who was then a graduate student in Caltech, Igor Devetak, who was various postdocs in professor positions, and now he's in Switzerland making a lot of money for investment banking, and Patrick Hayden from McGill. Okay, so here's the outline. And the outline already contains one of the themes of the talk, actually two of the themes. So this must be the background, right? I mean, you can insert the missing letters. This one here, maybe you don't know what it is. And this one's also not. And this one here, maybe you can recover again, because it looks a bit like English. It's what else? So they're looking ahead. So it contains two themes of the talk, namely data compression, such that you can recover the information because you know enough of English, and overcompression, which you can't, because it's not sufficient to know just English. You have to have some additional information to make sense of these acronyms. And I really this so-called mother protocol, I mean whatever it is, if you haven't heard of this before, the conceptual centerpiece of a lot of this work is the problem of characterizing the transmission of quantum information via a quantum channel. So quantum channel is just a sort of box where you have an input slot and you can send in some particling and in some quantum state, and then it has an output where the particle or the particles come out in a modified state. So obviously this is a device that you can use to communicate, and for some of them you can even communicate quantum information. So the basic problem of quantum channel theory, I would say, is to calculate the capacity of such a channel. But as it turns out, capacities are tricky things, and besides, on the side of this capacity question, also problems of data compression have been developed. So one thing that I wanted to take home from this talk is that data compression is, in some sense, it's the more basic, but also the more general. If you understand data compression really well, you can solve all these seemingly more complicated problem of fighting noise as a consequence. Okay. So the introduction background, it will be just a review of some quantum channel theory and also of some classical things that you might know or might not know. So if you know all this stuff, I beg your pardon to bore you. If you don't, so the better. So on this slide I have one thing that was already there in the previous talk, the von Neumann entropy of a density operator that's minus the trace of rho log rho. So Schumacher in the early 90s started looking at what would be a nice quantum version of the classical Shannon data compression problem. So in Shannon's data compression problem we have a source and of symbols from some alphabet. So he said, well, the source is similarly it's the classic object, probability, pi, but there is not an alphabet, but you have to pick pure states from some Hilbert space, which is going to be finite for us. So most important quantity there is, well, object is the average density operator. So it's a mixed state, or a mixture of all these guys. And the result it defines, after defining the problem in the correct way, is that the minimum rate of block compression, so that's the number of qubits you need per realization of the source in the limit of many samples, is the entropy. So instead of giving formal definitions, I'm just drawing a little picture, sort of a flow chart. So here are the states that come from the source. So the probability of this particular one is just the product of the probability pi1, pi2, etc. This stuff is all given to the compressor, so kind of Alice, always. So that's some quantum operation, might be unitary, might be completely positive, map on density operators. For rate R compression, we want that if she gets n states here, she has to map this somehow into n times R qubits. And in such a way that Bob, when he gets this stuff here, he has a matching decompressing operation that gives him n particles on the output, such that the joint state is very close or ideally equal to this one here. But in practice, well, for the sake of a good definition, we allow a small deviation. It has to go away when n goes to infinity. Yeah, so in case you never studied Shannon theory, this is a very typical setup. So you define a stochastic object, then you look at some sort of thermodynamical instance of this, which means many independent copies. And you have to work with these independent copies as one, as a block. And the benefit of n going to infinity is that for each finite n we're allowed to make a finite error, but the error has to go to 0 as n goes to 1. So then we can ask, so what kind of rates are possible? Obviously you can achieve some rates because this is a finite Hilbert space. So there will be some finite number n times r qubits that can represent this. So the minimum rate in Schumacher's theorem is this. Okay, so before we go on, I want to get rid of something that is a bit classical in this setting, which is the distribution over these pure states. So in a way, you don't want to talk about individual pure state and probability distribution. You only want to talk about states. So a nice way of this, for doing this, is provided by entanglement. You can, we have our average density operator rho. You can introduce a purification with so a pure state on a bipartite system such that the partial trace of R is equal to A. So R is called the reference system because it's just kept around to keep the state pure. And so here's the state psi, kind of is distributed to R and A, and this kind of one of the very first ideas that came up in the connection with entanglement, that whenever you have an ensemble decomposition of rho, so rho is a mixture of these pure states with probability pi, you can realize that by making an appropriate measurement on the other R multipliers. I guess some people call this theory in the simplest case. So what Schumacher looked at much more concretely is actually not a bunch of pure states coming in, but these n registers from the entangled state going into the compressor and coming out again here. And the reference stays on the side all the time. And what he really showed is, and what he really demanded, or if you want, what he really wanted is that this overall quantum state is very close to the original, which is psi tensor n. Right? So you can convince yourself, it's actually not a difficult exercise, if this is true, then also this will be true, at least on average. So you will look at the average distortion, and this one will be small. Okay, so I will even tell you how this goes because it's kind of the first element of the dummy course. So in these self-help books, Radada for Dummies, you usually go home with a bunch of slogans and mottos, the basic principles that you have to take to your own application. So here's the first one, and it's kind of this idea that Schumacher took from Shannon theory. So he observed that when you look at this density operator rho to the power n, there is this thing called the typical subspace, and it has various remarkable properties. One of them is it's kind of small in its dimension, it's governed by the entropy, so it's 2 to the n times entropy flow. And all the eigenvalues are not really equal, but sufficiently equal to say such a thing. So they're all in the range of 2 to the minus n times flow. And so this subspace, in addition, has almost all the amplitude. So I mean, if you measure the projector on the subspace versus the complement, you will find the state most of the time in the subspace. So, so the motto is, when you want to do Shannon theory, why do we get entropies? Actually, because we're looking at many copies of things, and in many copies, a state rho is not just a rho tensor n. It's really, you may always restrict to the typical subspace, and then it's as if the state was simply a uniform state. So all the eigenvalues are the same in the density operator in some large dimension subspace, and the dimension is exactly governed by the entropy. So it doesn't tell you exactly where this subspace is, but you don't even need to know for what counts. Okay, okay, maybe I should get back. So just to make sure we understand what's happening. So this compression operation of Alice is simply a binary measurement to determine if the system is in this typical subspace or not. So it's a two-valued measurement. And if it's not, well, then Alice just sends a default signal. If it is, then, which happens most of the time, then it's then the dimension is this here, so we can represent the subspace by n times s of rho many qubits by some basis change. Right? So that's how it works. And the inverse is simply the embedding of this subspace into the n copies of n. Okay, so all this was considered revolutionary, and I think it is because, for example, thanks to this paper of Humaris, we have the word qubit in not just scientific but everyday language nowadays. Just as Shannon managed to introduce the information value of a bit in his paper on information theory, so what he did then was something like this. So it's kind of much simpler, of course, than Schumacher. So we have a classical source. It's just a random variable x. We simply can take various values from a finite set with certain probabilities. And he was introducing a compression problem very similar to this diagram, to this one here. And he finds that, well, the optimal rate of compression is the entropy of x. So that's the Shannon or Boltzmann or whatever entropy, whatever you call it. So that's the classical case of the entropy. By a very similar strategy. So you simply find a set of events that are typical, has most of the probability, but each of them has about the same probability. There's not too many. Okay, so here's something that you might not have heard. I mean, I guess all these here that would have been in some kind of information theory introduction or even quantum information theory introduction, at least mentioned to some degree. So here is something that some people still consider as a kind of a specialized chapter in classical Shannon theory. It's a problem considered by Slepian and Wolf. So please try not to read what's here, or maybe you have read it already. So the thing is, in Shannon's compression problem, you prove some kind of optimality. You say Alice really has to send h of x many bits per signal. How is it possible? Well, it's clearly impossible to prove such a thing if Bob already knows the stuff from the beginning. Right? If he somehow has a way of learning the value of the source in some other way. So you have to suppose explicitly, if you want, that Bob knows nothing in the beginning of the game. And so when Alice does her compression, Bob sits there just patiently waiting with zero information. So what happens in a more general situation where Bob already knows something about the source? So true to Shannon, the most general way of modeling this is that Bob has some other random variable. So we're talking classical now, right? And we can relax, there's no problem sets here. No superpositions and no entanglement. So he has some variable y that's correlated in some known way with x. So this might be, for example, if x is a large number, this might be the parity. But it might be also some statistical information. If x is a random bit, then y simply might be a noisy version of that random bit. It might be flipped with a small probability. So all this constitutes some kind of prior information, right? So the situation is that Alice sees x, Bob sees y. They don't see each other, usually other parties in the variable. So what Slepian and Wolf discovered in 1971 in a beautifully written paper is that the optimal compression rate is given by the conditional entropy, which should be, I mean, I didn't even write all the definitions, it should be clear what this is. It's for each value of y, you have a conditional distribution of x. which is an entropy, and you just take the average. It turns out that this conditional entropy can be written as a difference of two entropies, which is going to be very useful for us. It's the joint entropy minus the entropy of y. So why is that surprising? Well, okay, so let's try to explain this to ourselves. So why is, for example, why can't you do better than this? Is it somehow surprising that you can beat this lower bound? Well, actually not, because that follows simply from Shannon in the following way. So there's this small black thing down here. Alice and Bob could have gone into a game of transmitting both the pair x and y by first sending y, which costs h of y, according to so I didn't write it out. So first sending y, which costs h of y, and then sending x, which costs some unknown rate. But at the end of the day, both will have x and y together. So by Shannon's theorem applied again, the optimality of this joint protocol will, well, it will say that this h of y plus this unknown rate r has to be at least as large as h of xy, right? So that gives you a lower bound. So on the other hand, so maybe it's surprising that this can be achieved. Let's assume that Alice also knows y. So both Alice and Bob get to know y, and then Alice only sees x. Well, also then it's kind of trivial how you achieve this, because given y, Alice and Bob know what kind of distribution they share. So then we're back into Shannon's scenario, right? And then we're just sharing samples from a known distribution. So, and that can be compressed to h of x condition y. Fine. So the surprising and truly non-trivial component is that this can be achieved without Alice ever knowing y. In a universal way, if you want. She doesn't even have to bother. Okay, so here is how it works. Actually, unfortunately, to this day, there is no explicit description of doing this. There is a recipe of arriving at such a protocol, and it's as follows. So, okay, let's first go through this as follows. So, we want to view this side information here of Alice as basically the output of a noisy channel, where the input is x. Right? I mean, so that's kind of, I think that is the idea that Snedden and Wolf introduced into this. You want to infer from looking at y, and of course some extra information which has to come across, you want to infer x. So these kind of diagrams here is the same kind of flowchart, only that now Alice occupies the region up here and Bob down here. So initially x and y are distributed, well, it's kind of in the past. Then Alice has to do some compression, right? She wants to send n times r bits here. And Bob just, has this y and waits patiently until this stuff comes along, and then he has to decompress, taking into account both of these things, the message and the y. So what comes out, of course, is ideally an estimate of x, of the string x, and well, here's y. So but out of pedantry, I just wrote that he has to keep y around because he wants to know both. So we apply the first lesson. We only will pay attention to Alice's typical sequences. So there are 2 to the n entropy many of them. So these are the only ones we need to worry about. And the protocol will do the following. So see, we have to find a mapping that has this many possible messages, right? If it consumes n times condition entropy many bits, then 2 to this number is the space of messages that we can choose. So this mapping here will be in general many to 1. It will map so many messages into so few bits, and we construct the map in a random way. So I just tell you how to find a particular instance. You simply assign a message value for each individual typical string here. For the non-typical ones, you just forget it because they don't happen anyway. So now, as I said, what we do is we view y as the output of a channel, which we always can thanks to base rule, I guess. We can write the joint distribution of x and y as the probability distribution of x times the conditional distribution of y even x. And in the conditional distribution, that is just a noisy channel in Shannon's formalism. It simply is the rule how likely a transition from an input state x to an output state y is. Okay, so thanks to this random binning, what we happen to achieve is each bin, so the pre-image of each message, if you want, is of size, well, this divided by that, right? You have a large number of objects, you throw them randomly in bins, typically occupation, and actually with high probability, all the bins will be occupied with a number that's basically the ratio, small fluctuations. So each bin is this large. Okay, so now let's go through the whole diagram again. So now Alice will tell Bob, so they both know what the mapping is, right? So they know what the association of messages to bins is. They have to agree on that somehow beforehand, or thanks to the shared randomness, thanks to the randomness that you might share to construct the mapping. So Alice does this and sends Bob the bin. So what does Bob learn from this? He learns, well, Alice's X is one of so many messages. And you can take I simply as being defined as the difference of h of x minus h of x condition y. It's known as the mutual information. So he learns that x is one of these many messages. And they are random, because the bins were constructed in a random way. So by Shannon's second theorem, the one that governs good channel coding, we learned that, by invoking a big hammer here, and we are learning that random codes of this size can be decoded well, obviously efficiently, in the sense of small error probability. Yeah, so for this channel, P, Y, condition X. So I just have to rearrange the words every time I go through this, because now I'm going to say the same thing again. I'm saying, okay, so Bob learns in which code Alice's input to his virtual channel is. And he receives the output. He got it from the very beginning. So then he can just apply the decoding algorithm to this output, and he will recover X. Bingo. So, let's see. No, that's not it. So I showed you a proof that invokes kind of classical channel stuff, the data compression and also the channel coding. So the beautiful thing about this proof is it also goes the opposite way. Assume that you have a way of sending, of solving this Lyapunov data compression. So two mappings C and D, so they're just combinatorial mappings, such that here only n times h of x condition y bits go across. Then I claim you will recover Shannon's channel coding theorem. Why is that? Because we still have this channel here, right? And this channel can be anything. I mean, depending on this problem, it is something. So if we have only, if the mapping will have to map all these many typical sequences into so few bins again, so at least one of the bins, in fact, most of the bins will have a size at least as large as this one here. And we assume that Bob will be able to recover from knowing which bin, so knowing which code, in other words, and the output of the channel, what the input of the channel is. Okay, so in other words, most of these bins constitute good codes, and most of them are actually large codes. So they allow you to transmit n times the mutual information in many symbols. So if you had a way of proving this Lyapunov theorem directly by other means, you would actually recover Shannon. And there is such a way. There's a very beautiful proof by Tom Cover that, in fact, I think took this random binning literally and just went through the analysis straight away. So in a certain sense, this Lyapunov theorem and Shannon's second, so the channel coding result, are equivalent. They're just two different ways of representing the same fact. But I think data compression is slightly more, it's kind of a nicer way of thinking about things, because all you're worrying is to reconstruct data. There's no noise amplifier, there's no encodings in a way. All you're doing is just changing the representation of your data so that at the end the receiver gets all of it together. Okay, so this particular way also proved to be very fruitful for the quantum case. That's the other reason why I want to emphasize this point, because for a long time, we didn't actually quite solve this problem of transmitting quantum information via quantum channels. But this one, it looked a little bit simpler. So after background section, we have FQSW, which is fully quantum Lyapunov. It's a word that we basically inherited from the earlier literature. It's just quantum Lyapunov. So we basically quantize this whole thing here. So So all the lines, they have to be qubits sitting around or traveling between the parties. And all the maps, they have to be represented by quantum channels, maps, quantum dynamics. Okay, so here goes. Oh yeah, and according to the lesson number 0, instead of talking about the source as a bunch of pure states, we actually think of it as being part of one big pure state, where the one half is held by the reference and the other half is given to the players. So this is the diagram that represents the quantum state. So the lower 2 bits, that's Alice and Bob here. That is something that we knew before. So Alice gets the state, something from the source. She has to do something to it and send a number of qubits to Bob. And then Bob, together with his half, his part of the stage side, and what he gets from Alice, he has to do another thing to get out B1. So these objects here, they, if I just look at this line and going out here, and this input and going out here, these are in general completely positive maps, but we know from very old theorems that any such map can be actually viewed as a unitary on a larger space if you introduce the appropriate ancillars. And so I want to do this here because since we started off in a pure state, it pays off to maintain the pure state, just following what's happening to this pure state as you go along. So this map of Alice, it has some ancilla. So Alice's transformation is simply bringing her input state in contact with some ancilla initially in a pure state, and then keeping this ancilla around, whereas she sends the other stuff to Bob. And similarly for Bob, he gets his input from Alice and from the source, and he has to produce something here, but he keeps also some ancillas around, because generally this will be a completely positive map. So these are unitaries, and it's mathematically these are isometries because the Hilbert space dimensions don't have to match, it's just embedding. Anyhow, at the end of the day we still have a pure state. What's the task? And we can of course draw such diagrams whatever U and V are. What we want is that the reference and the stuff that Bob has, namely this register, that we have to split up again, which I didn't do this here, I have to split it up into 2 actually, there's an A hat and a B hat. These 3, they will contain a quantum state that's defined by the evolution that we're following here. And this state should be very close to psi. In fact, of course, I should have said we want to look at the many copy situation. We don't give up this Shannon theoretical point of view of compressing blocks of n and then go to infinity. Okay, so if you look at only diagrams of the sort where R, A hat and B hat, so the first and the last line, are in a state very close to psi, in particular in a pure state, how many qubits do we have to send here as a function of the source? Okay, before we go to this one here, I should also, that's the question. How large is this register A1, the number of qubits, or the number of qubits divided by n? It pays off to also look closely at what happens to these junk registers. I mean, I call them just ancilla, and you would think Alice and Bob just tossed them away because they shouldn't have nothing to do with the source. But there's kind of a cute thing going on here, because you see, since the overall state is pure, and R, A hat, B hat is pure, or almost pure, it means that A node and B node must be also in the pure state. So the global state at the output is actually a tensor product between this R, A and B hat and A node, B node. So in other words, this here must be some pure entanglement left over between Alice and Bob. So it's kind of a cute thing. So whenever you have a protocol that does such a thing and has non-trivial leftovers for Alice and for Bob, these leftovers are actually not just junk, they're the opposite of it. They're quite useful at the end of the protocol. I mean, when you think of this is what we are discussing here, very simple games of information processing. I mean, Alice and Bob are given some prior information. Alice wants to somehow shuttle her information over to Bob. Well, that will eat some resources. She will have to send some qubits. But at the same time, they gain some resource. They gain entanglement that might be used later for something else. Okay, so instead of beating around the bush for too long, I want to just give you the answer. So the number of bits that we have to send is this here. It's half the quantum mutual information between Alice and the reference. Go back. So when I write mutual informations, it's always with respect to the initial state. So it's a three-party state. So it has, there's an entropy of the reduced set of R, of A, of B, and of joint system 3D, and so on, AR. So the minimum number of qubits we have to send is half the mutual information between Alice and R, Alice and the reference. This makes a lot of intuitive sense, because this number measures how correlated Alice and the reference are, so kind of how much Alice knows about the source. And at the end of the day, the amount of entanglement is this one here, so it's half the mutual information between Alice and R. So to write such things, and for later use, I could have written, the optimal resources are the following, but I chose to use this formalism that was introduced in very painful detail in a paper with Igor Levitek and Aaron Harrow, which might be amusing to you at any rate. So in this information theoretical game, so we're dealing with lots of different objects. We're dealing with tripartite states between Alice, Bob, and R. We're dealing with channels. We're dealing with entanglement, and we're dealing with what we call coding, which I never really say what it is or how complex it is. Let's say Alice does some completely positive map, or Bob does some completely positive map. So these correspond to the encoding and decoding transformations in classical channel theory. So we realize we can think of what we're doing in information coding as some kind of transforming resources in some organized way. So in the quantum Slepin-Wolf problem, what we're given is a resource and many copies of this tripartite state. So I will just introduce a nice little picture for this. And we write curly brackets to say it's the resource associated to this state. And then we have particular resources that are kind of singled out, for example, the noiseless qubit channel. So that's the resource of transmitting one pure qubit. That's this one, Q arrow Q. And then we have also another cleaning resource like an EPR pair, one bit of entanglement. So that's this thing. So starting off with this state and so many noiseless channels, which we want to use somehow. Whereas we want to combine them in some way where only local actions are allowed. And so the local actions are something like this U here, and then the channel is invoked, and so on. So up to these local, unlimited local operations, they end up simulating in this way. So when the black box behavior of this protocol is simply that Bob has the state entangled with R, not Alice and Bob together, but Bob only. Alice is kind of left out here. Plus they have some entanglement left lying around. And so we call them resource inequalities, but I really think of them more like chemical reactions. And so you throw together certain ingredients, you stir them, and out comes this here. And what stirring means, it's given by the rules of these information games that only operations are allowed, but then all of the operations are allowed that are purely local. Only at Alice, only at Bob, maybe only at Charlie if you have more parts. And so, of course, you can formulate lots of Shannon theory in this language. You can write down, little formulas like this that express transmission of information via channels assisted by unlimited entanglement. Because then you just write the channel here. That's another resource. You write infinitely many EBITs. This is larger or equal than a number of uses of a clean qubit channel, and you want to know what this number is, and so on. Okay, so let's get on with our problem here. So this is just a nice little formalism to write these things. Okay, so the notes here. We get, I said this already, whatever the protocol succeeds in doing, we get some entanglement out. Because there's this pure set between A node and B node. And the other remark is you know, when you look at the classical Seppian-Wald problem, the resource of the source, so the distribution of x and y, that is just a way of formalizing the task. I mean, given these data, Alice wants to transmit y, x to Bob, who is only y. Here it's a bit different because this is not just the task. It just doesn't describe what you have to do. It also describes, in a very deep and confusing way, a resource in its own, because there is some hidden entanglement between Alice and Bob. So sometimes, if the state is the correct one, this number here, the number of qubits you get out, might be strictly larger than the number of qubits you invested first. So you couldn't have generated, if you do without this here, you couldn't have generated this amount of entanglement, because you simply couldn't communicate as much. One bit of communication can only create one bit of entanglement. So there is some kind of entanglement distillation going on as well. And then there's something really interesting going on in this problem, that these two aspects are somehow completely inseparable. Okay, so I'm just kind of repeating things again, like in the classical Seppian-Wald problem, so that eventually we can see how the solution comes about, why it's almost obvious. Well, after you work on these problems for about 2.5 years, I guess with some embarrassment I can say that it becomes a bit obvious. But and so I really hope that eventually everybody else will agree with me and stop me from giving talks like this and trying to explain it again. Okay, so let's do this whole diagram in a different way. Just write two stages, before and after. So before, we have the three-part state, and they can also, I mean, what Alice does is just a basis change. And she has this unitary that somehow maps the A system into two slots. The one she will keep, and the other one is about to send to Bob. So they cost her a number of Q qubits. At the end of the day, R is only entangled with Bob, because Bob has the full state. And A naught and B naught are pure entanglement. So there's a trivial consequence of this. A naught, so what Alice is left with, and the reference are completely correlated. The quantum state describing these two systems is just a product. And that is already the key to the lower bound. To see that you cannot beat this half-mutual information. And it's a very simple one. You just use elementary entropy inequalities to convince yourself that for each qubit that Alice removes from her system, so that she has to send over, she can decrease the mutual information with R by at most 2. At most 2. So she has to go from some situation where she has a mutual information with R to a situation where it's 0, because the product state. So by sort of conservation law, it means that the number of qubits she had to toss out from her system and give to Bob is at least half the mutual information. Okay? That's very easy. And in a similar way, by looking at the entanglement that exists between Bob and the rest of the players in this game, you can also see that the entanglement is also kind of optimal. I don't know if I want to go through this. Well, it's okay. Let's do it quickly. So initially, the entanglement between Bob and the rest is just as measured by the entropy of entanglement. It's just a pure state is S of B. In addition, of course, he gets this system here, so that it might, in addition, carry n times q many. Actually, I need to put the n here. So it might carry q. It's q qubits, so it might carry q qubits to him. And then he does some local operations, so it cannot increase the amount of entanglement, but at the end of the day we have a very simple situation. Again, the amount of entanglement is just the sum of the entanglement here with the reference and plus the stuff here with Bob, with Alice, Bob with Alice. And that's E plus, well, S of R. So we get that S of B plus Q is larger or equal than S of R plus E. And if I rearrange the terms, I get this one here. The difference between Q and E is lower bound by the conditional entropy of A given B. Which might be negative, of course, but I mean, we don't care. It can happen that there's more E coming out as Q going in. So, and of course, when you think about it, you can't hope for anything better. I mean, you cannot prove that E is bounded by something. If you if you allow unlimited quantum communication, you will also be able to create unlimited entanglement between Alice and Bob, just by Alice preparing an EPR pair and sending one particle and repeating this as many times as she wishes. So for each qubit you give more here. For each unit you increase this one, you can also increase this one by 1 unit. So that's why the best we can hope for is a lower bound on this side of this one. Okay, so and so by just looking at these conservation laws, if you want, we learned that the optimal protocol of such thing, I mean, this with certain numbers Q and E always can be done clearly, because Alice could just take her Hilbert space, stuff it in some qubits and send it off. I mean, it's always possible by Schumann. The minimal protocol in some sense is the one where Q is equal to what I wrote before, half the mutual information between A and R, and E is half the mutual information between Alice and Bob. Okay, so just a small thing. So the size of the sizes of these systems, they come. So I mean, the number of qubits is really just the number of qubits of the system A1 that she wanted to send in the whatever picture. Where was the picture here? This one here. And the size of A0, that's what she just leaves behind. So conveniently, the sum of these two is S of A, which is just the amount of qubits she needs to store her part of the source by Schumann for data conversion. Okay, let's see. How am I doing with time? I should probably try to go on the last lap very soon. Yes. So I will discuss a little bit how this is achieved. So looking back at the classical set of work, it won't come as a surprise that I cannot describe a protocol to you explicitly, but some procedure how to select one at random, and then you can prove that with high probability this protocol will do exactly as you want. So it's a typical random coding algorithm. So what we do is simply splitting. So Alice's typical subspace. So this is A tilde. It's some subspace of n times S of A qubits sitting in her n Hilbert spaces. So first of all, she just cuts down to the subspace. So she performs the first step of Schumann's compression. And then she simply splits this Hilbert space randomly into A0 and A1 with these sizes. So A0 has size n times this number of qubits, A1 has this number of qubits. Randomly means she applies a random, okay, so you can think of A tilde as being a number of qubits. And A0 is going to be the first block of qubits, and A1 is going to be the remaining qubits. So this random splitting is then simply applying a random unit. And then you have your split already. It's given by 100 qubits divided. So then how do we analyze this? I mean, how do I show that okay, I kind of told you, okay, so Alice has to somehow split up the system randomly. So the difficult part remains, how do you find this V here? Bob has to somehow put together the information and recover the entanglement and recover the entanglement with Alice and so on. How do we go about that? Well, that's kind of another of these little lessons to take home. We don't have to. We don't have to worry about it. So in the analysis, we do not have to, for each V, to come up with, for each U to come up with a V that somehow maximizes the fidelity to this kind of situation. All we have to do is we make sure that R and A0 at the end of the day are in a product state. So this is, quantum coding by destruction. All Alice has to aim for is destroying her correlation with the reference. She has to, she has to be able to forget everything she ever knew about R. In the spirit of Lorenz's talk. Why is that? So I'm claiming that once she's forgotten everything about R, by force, Bob will know everything about R. That's something truly quantum, right? In the classical world, it's not sufficient to burn all your letters to make them appear in the newspaper. So usually you have to do much more than that. So in quantum world, it's much more beautiful. So why is it sufficient? Well, so let's say R and A0 are in a product state. Well, we know that by the way we wrote this diagram, at the end of the day, this is all a pure state. But as a pure state, it means it's a purification of this product state up here, R rho R tensor rho A naught. And so, sorry, not at the end of the day, at this stage here, where the red line is. So we just made sure that Alice managed to decorrelate herself from R. So we know that, well, the joint system A1 and B, that's somehow a purification of this state. But we know that all purifications are equivalent. This one here that comes out of Alice's lab, and the one that we aim for, which is simply the purification of R, tensor with the purification of A naught, which is a particular one for a tensor product state. So there's a unitary connecting them, and that's the V. So this unitary simply exists. I mean, you can employ a singular value decomposition on a huge matrix to figure it out, but we don't know. We don't need to know this for the analysis. All we need to aim is decorrelate them. Then we are sure that Bob can decode. Okay, so that looks much easier. So we basically what we have to do is for each unitary that we pick here, we have to somehow introduce some kind of distance measure of the actual state between R and A naught from the tensor product state. And in the analysis you have to show that if you integrate this distance over the unitary group here, and A1 is slightly bigger than the half dimensional information, A naught is slightly smaller than the other half dimensional information, then this expected difference will go to 0. So that tells you that for most of you, the difference will be small. Okay, so I guess I said this again. So that's something peculiarly quantum about transmitting quantum information, to make sure that a particular agent has some quantum information. All we have to make sure is that nobody else has it. I mean, if it's around, so quantum information in this world is simply always, it's some entanglement with a completely inert reference. There's always this R sitting around. That defines what the information is. And R is entangled with all the other agents in the game in some predefined initial state. So all they are allowed to do is, splitting up systems, sending around qubits. It will always be a pure system. It will always just be a different purification of the initial rho R. And this is the slogan. So to make sure that Bob has the system, all we have to make sure it's not left in Alice. Okay, so no details. It's all calculation.
But
so
you have to make sure it doesn't correlate with anything else outside. Usually, it's important to keep everything.
Yes, yeah, okay. So it's kind of simple enough here, right? Because we have at most 5 registers that any given one. So that's true. Yes, yeah, sure. Yeah. So the calculation is somehow instructive, but on the other hand, it's some parts of it are purely technical. So maybe I'll save you this one. Also in view of time. No. Okay. Yeah, so random coding is okay. If I had another lecture, of course, I would also explain the random coding to you. No mercy. It's also elementary in the end. It just relies on a few other small tricks that can be used indefinitely in other problems of similar type. So what I want to say is all the things we did so far, they were kind of really general purpose ideas. I mean, they originate in connection with this particular problem, but I think I'm trying to stress them as general principles because that's what they are. Okay, so so here's the resource inequality again. So we have the state plus some quantum communication the state goes to Bob, and some entanglement left over. So we should kind of try to understand how general this is. What kind of situations is this capable of describing? Well, one of them is clearly the Schumacher compression, because that's when Alice and Bob has no information initially. So the state is just a pure state between Alice and R. Then half-dimensional information here between Alice and R is Alice's entropy, and the other one is 0 because Alice and Bob are in the product state. Fine. Can I give another good one? Yeah, for example, if psi is a GZ state, So that doesn't really have entanglement between Alice and Bob. And if you just trace out a reference, it's a separable state. Nevertheless, these quantities are non-trivial. You're left with half a bit here, and here have half a bit here. So you only need to send 1 qubit every 2 instances of the source to transmit it. And you get some entanglement out, actually at the same rate. So this coherent communication somehow is used catalytically because you're left with the same amount of quantum coherence. Okay. So that kind of leads me to the next part of the talk, which is this one, the family. That's because we have this inequality, so we can just kind of apply another chemical reaction to this bit here. I mean, we could use the entanglement, for example, or we could get this stuff in a different way. Maybe we have some way of making these quantum communications from other resources, like in teleportation. Since everyone has to mention, I guess I should say, teleportation can also be phrased in this nice way, obviously. So one of the things that we can do, another thing that we can do is, because it's all just applying unitaries and sending systems around, we can just run the whole field backward from, well, I can't go back to the diagram, it's too far away, from this side to that side. And that gives us yet another protocol. So by doing all these things, by running time reverse, by concatenating it, we get a whole bunch of different transformations, some of them which are familiar, and this is the family tree. So this is the thing we just derived. The time reverse is this one here, called quantum reverse Shannon theorem. And then there are things like the original mother, something called the father protocol, something called the merging protocol. Lots of things down here. For example, the quantum communication via quantum channels. Or the mother generates something called entanglement distillation from noisy states. So given a mixed state, and you want to see how many pure impurities you can extract. So no, this one not. So for example, this one is the mother and just an example. This one. So the mother, the original mother, this is some paper with Aaron Harrow and Igor Debeta. Basically, back then we were doing these things without looking at the reference too much. So it was a bit stupid, but if you just ignore R, then at the end, well, at the beginning, Alice and Bob have some non-trivial state together. At the end, they have a product state, so that's something we don't even have to mention because the product state is simply local resources. So given this state, plus some amount of quantum communication, they end up with some amount of entanglement, which is, as I said before, already non-trivial if this number is larger than this number. So this is something that's kind of in quantum communication assisted entanglement distillation from quantum states. And then you can combine this simple thing with other simple things. For example, getting this here by teleportation, so you have to invest a number of classical bits and, well, twice as many classical bits and the exact same number of e-bits to make it, right? I mean, for teleporting 1 qubit, you need 1 e-bit and 2 classical bits. Then you get, and you amortize the entanglement. You see on the left-hand side you will have amount of entanglement, on the right-hand side you will have an amount. So you get this here, the state, plus this specified amount of classical communication from Alice to Bob, results in the difference of these two mutual informations, many e-bits being distilled between Alice and Bob, which is this number. It's minus S of A condition B, which is also has it goes by the name of coherent information introduced by Ben Schumacher in the 90s. And this whole thing, it somehow includes a way of distilling entanglement by local operation classical communication from mixed states in a near-optimal way, because it was long conjecture that this is achievable and it gives you some kind of coding theory. No, we don't do the father, we do state merging. And it's a similar thing, so going back to the mother, we don't forget the reference. So as I said, we can do the quantum communication by teleportation and amortize the amount of entanglement that's on the left and on the right. Now I choose to put it on the left. So the state plus amount of classical communication. Let's forget about this for the moment. Just think of the classical communication being free. You will still need to have be able to transmit some coherence in general. And the amount of entanglement you need in assistance is just this one. It's just the conditional entropy. So it's kind of suddenly and unexpectedly the original Slepie-Wolf problem comes back to us. You know, in the classical world, that was just the answer, right? Alice and Bob had this joint source, and for Alice to transmit her share to Bob, the amount of communication resources was just the conditional entropy. So that kind of comes out again in completely different guise. Now it's a situation where, okay, we want to transmit quantum information. The communication is actually unlimited, but it's only classical. And then the conditional entropy still is there, but is quantifying the amount of entanglement you need to facilitate this. Okay, so I think I'm near the end, so I don't want to go through all the examples of protocols. I wanted to highlight some kind of future developments, so this may be leading a bit too far. So here is all sorts of questions. So I want to kind of end on two questions. One of them is in the slides, the other one I was in fact reminded only during the break in the conversation with Prakash. So this one here, that's what you will actually find in Slepie-Wolf's original paper, the distributed compression problem. So the way I formulated this was kind of asymmetric. Alice wants to send something to Bob, and Bob already has such. In the distributed setting, you just have two sources, Alice and Bob, and they want to send something to a receiver, who is a third player, who knows nothing initially. So they have this state. At the end of the day, the receiver should have the information. So the quantum version, as we know how to model this, is just have this tripartite state. Initially, they can send some qubits and leave some stuff on the side. And at the end of the day, Charlie should be able, by some local unitary transformation, to get the entanglement with R and maybe some remaining stuff. So you can ask the question: what's the achievable rate region? For each pair of numbers QA and QB, you can ask: is it possible to do that? And you can map the region where you can. So there are certain trivial observations you can make about this, and it's just following what also Slepie and Wolf are doing. For example, it's it's convex. Why is that? By time sharing. If you have 2 points, then you can run the one scheme for it realizes 1 point half the time and run another scheme half the time. Then you achieve rates which are just a convex combination, the midpoint between these 2 points. It contains, via what we know as quantum state and Wolf, these 2 points. For example, Bob can send all his stuff using S of B many qubits, and Alice can do her part of the quantum state and Wolf problem. That's this half-mission information and vice versa. And we know, of course, that we have lower bounds like this here. And that's pretty much all we know. So kind of what I want to kind of flag here is as an open question: what is this rate region? What are the possible pairs of rates at which you can locally compress a distributed source? So in the classical case, the Slepie and Wolf result gives you already the answer. The region is given by these 3 inequalities. So we discussed already each rate individually has to be at least the conditional entropy. Together, that's another easy one. They have to be at least as large as the joint entropy, because what they achieve jointly is in the end compression of x and y together. So when you look at the corner points of this rate region, for example, this one here, there's h of x and the conditional entropy, and vice versa, h of y and the other conditional entropy. And we know how to achieve them. That's just the Slepie and Wolf thing that we discussed in the very beginning. So in the quantum case, it's not as nice as this. Of course, we have bounds like this also, right? In the lower bounds, we have something, and for the rate sum, well, it's at least as large as Schumacher, S of AB. But when you look at the fully quantum Slepie and Wolf protocol, it's actually worse than that. If you just add up the rates of that, this here plus S of B, it's not S of AB, it's slightly more than that. There's all these additional terms here. So for this expression, we introduce an abbreviation, J of AB. And you can see that in general this is not optimal, because it measures somehow the local noise, the local entropy of Alice and Bob. So there are cases where this is simply too big. For example, if Alice and Bob register have somehow split in such a way that there is this pure entangled state sitting around, there's no reason why they should send it. but it shows up in the entropy calculation. So there are cases where you can achieve rate sums strictly smaller than this. So for this purpose, we've developed some kind of lower bound, which is this one. So the sum of the rates is half of this J minus a particular entanglement quantity of the state shared between Alice and Bob. In particular, it's 0 if the state is separable. So in this case, this lower bound is optimal. But in general, we have this situation. So we know that the rate region is contained in this pentagon, this vertical, this horizontal, and this diagonal line, the red one. We know these two black points that are strictly above the diagonal. These are the fully quantum Serbian Wolf protocols. And apart from that, we only know that it kind of goes here, 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 and then maybe extends a little bit. We don't, in particular, we don't know if it touches this line or not. So I think this is a very beautiful and fundamental problem to find out what this correction term here is. And if it is really related to the entanglement of psi and E. I mean, it must be, but in which way? So we have these bounds, an upper bound where the correction is the 0 communication distillable entanglement, just by doing this here, and a lower bound where the correction is another entanglement measure. But so is there some entanglement meaning to the minimal rate sum? So okay, so I think this is what I wanted to say. Indeed. Oh yeah, this is not what I plan here. Ah, this is even better. So okay, so great. So the other problem, if I may, into the discussion time, is going back to this resource inequality business. So what we did there was we associate an abstract entity to each channel from Alice to Bob and to each state shared between Alice, Bob, and the reference. And in such a way that this abstract entity, that is what is called a resource, is an element in a vector space. And this inequality sign that I mentioned, that I was writing in the resource inequality, that is actually a pre-order in this space. I mean, you can have that A is largely equal to B and B is largely equal to A, but the abstract entities are different a priori, right? So that you can have the ordering tells you certain things are equivalent. You can also, so it's a vector space because you can multiply things by constant factors, by positive and even negative values. You can add them and so on. So the question that I have, which might be much too hard to address, is what is this vector space and the order structure? So it's of the quotient. So you just divide out by the equivalence relation induced by this pre-order. Then you get a quotient space that has then a well-defined partial order. And I want to know things like what's the dimension of this? Because initially we start off with uncountably many objects. But then also the equivalence relation will identify potentially uncountably many things. So it's not very clear how big these objects are. Are there nice bases in which the positive cone of the order relation looks kind of neat or something. So all we know at the moment is certain inequalities, right? I mean, the quantum information theory is about establishing inequalities or finding the best inequalities for different resources. But I mean, ultimately, quantum channel theory is understanding this whole cone as some global object. Okay, and here I stop. Thanks for your attention.
Questions, comments?
In quantum Serbian Wolf, of course, you're considering that the thing that Bob has initially is like quantum information, and it's used up when you do the V unitary, so at the end that goes away. What if that is class though? Do you have some idea what happened if that part is?
If he has classical information,
yeah.
well, I have some ideas, but it's an unsolved problem.
Okay.
So So, I mean, on the question itself, I should like to comment a little bit, because it's actually not quite true that it's eaten up. So I want that Bob recovers all the information.
Yeah.
So not just Alice's, but also what he had initially. So that's why for Sven and Wolf I insisted on having two art reports, one for X and one for Y. So you change the problem already if you only want that Alice's information somehow arrives here. If you somehow are not concerned about Bob destroying the part of his information. So I think that we change the problem already.
What I'm
Anyhow.
saying is that Bob's information is not anymore what it was at the beginning, because it gets entangled with what Alex is.
No, you should really, I mean, at the end of the day,
Yeah.
up to mapping the information into different particles, Bob will still have this register here.
Sure.
Only that he will have another register that contains this one. I mean, he was entangled initially with Bob, with Alice in the reference, and all that happens is that somehow, in some subterranean way, the Alice's register made the way from her to him.
The information on these sides is
Yeah.
there.
Yeah. Okay, so your question is about what if the initial situation is just a bunch of entanglements between Alice and R, and Bob knows which state it is. So it's Bob knows classically which of the states.
Right.
So in general, we know that you have a smaller rate. So sometimes you can have strictly data rates in this situation. But as far as I know, it's not known what the answer is. I mean, the best lower bound is simply the conditional entropy. So the entropy of Alice, quantum, the entropy of the von Neumann entropy of Alice conditional in Bob's knowledge. And I have this long-standing project to prove that it's achievable, but maybe it's not even true.
I reckon is it true that there is a sense in which the quantum case is actually simpler than the classical case? Because you just said it's some sort of qualitative thing you need to establish.
Yes, yeah.
So you would imagine that there is some sort of more qualitative view on, maybe underlying even resource calculus, I don't know.
Well, I mean, in a sense, yes. I mean, in a way, of course, we're using the Hilbert space formalism to reformulate the task. We say, well, instead of proving this, to prove exists U, exists V, we only prove something about the existence of U with a certain property, and then V follows automatically. So maybe this can be used in some more complex situations too. And it is true. It is a tremendous simplification. Right? It's something that makes Shannon's channel coding theorem still quite some challenging thing to understand and to teach to people, because you will do the same. You say pick a random code, but for each random code you will have to describe explicitly a decoding procedure, and then you have to analyze the joint behavior of these two things as you vary the code. So, in describing this decoding procedure and analyzing what it does is not at all trivial. There's various different ways of doing this, but all these analyses they are more or less demanding. Whereas here, all we're saying is, well, destroy correlation. That's wonderful.
Yeah, so there is a sense in which I think that some people have talked about things like linear logic, that sometimes looking at things in a different way, like looking at linear logic makes classical logic more easy. So these categories people have been thinking about, the quantum is actually easier than the classical. Classical is some weird projection where things, it's like with complex analysis. Complex analysis is simpler than real analysis.
Yeah.
So that's what you're suggesting. Probably.
Oh yeah. Well, one caveat, of course. I was presenting this as a quantum version of certain work. It's actually not a generalization. So it's a different problem. It's the way many quantizations go. So it's a quantization that doesn't recover the classical Euclidean work problem as a limit, unfortunately, or as a special case.
Any other questions, comments? No, thanks, Andreas, again. And so we had a discussion session.
Yeah.
Now, I don't know what that's supposed to do.
To have a fight.
To have a fight. Who with who?
love each other so much this year.
So I can just announce one thing for those who don't know. Next year QPL will be in Oxford, co-located with MFPS. And
Dates?
what?
Dates?
The dates are fixed, but I don't know when. So it's quite early. It's quite early.
Early April, I think.
Yeah, it's very early. And this will be some Mike Mislov special because he becomes 60.
65.
55.
65.
65. So, and maybe one question I would have, since and maybe actually a question directed mostly to Peter, would be whether people are happy with the sort of change of format of QPL as compared to previous ones. Scope, content.
It's much better than previous ones. Yes.
I love it. I'm very happy.
Who was the previous one?
Not a student in the room.
Quantum lambda calculus is a lot.
The previous ones, I think, emphasized programming languages much more,
Yeah.
which was probably a reasonable thing at the inception of the subject, when we didn't have an existence and an identity.
I think foundational tools are quite well, maybe.
What?
Foundational tools are quite well, so maybe you could have more.
I would have liked to have more foundations, and I've sent this out to a lot of people in foundations. And some people said they would have liked to come if blah blah blah, there was no clash with something. It's not also the easiest place to reach. Maybe if you're a place like Oxford, which is closer to the continent, might actually attract more people in foundations.
But by foundations, you mean foundations of quantum mechanics?
Yeah, definitely. We should have more people of that. So, rightly. We have some people. We have a lot of new faces here. There's Andreas.
Yeah, I probably wouldn't have come to a quantum programming language workshop, but this is very interesting. Yeah.
It's a love fest, we can't fight.
What?
It's a love fest, we can't fight. That's one of the advantages of quantum programming language. We got plenty to fight about.
I have nothing else to say. And
Well, I'd like to thank everybody for coming. As we've been saying several times in the last few minutes, it was a fantastic workshop. Incredible diversity of different people, new people like Andreas, and in addition to the old suspects. And a whole bunch of young people, which is awesome to see.
an exceptional bunch of young people, I would say.
A whole bunch of exceptional young people here.
An exceptional bunch of exceptional young people.
And I think we should all thank the organizers and the organizing committee, and especially Prakash and Tom.
All right.
Okay. Just this is your last chance to get some more proceedings if you want.